Here comes, oh, you started it? Here comes telescoping series. Finally, a special type of series. Telescoping a series. Okay, here it comes. You ready? Let's say I had a series that looked like this. The sum is n goes from 1 to infinity of 2 over n squared plus n. Okay? Whenever someone gives you a series where the denominator is like a second or third degree polynomial that factors, but on the AP exam it'll almost exclusively be second degree. If the denominator factors, then you get to do telescoping series, okay? So let me just say that when the denominator factors. So this series can be rewritten like this. 2 times n times n plus 1, because the denominator factors. And at this point you go, I'm going to do something clever and tricky. I'm going to express this fraction as something over n plus something over n plus 1. That is, I'm going to do this sort of thing, you know, like you have 7/12ths. And you end up going, well, I can do a bunch of mathematical machinations, and I end up with 7/12ths is the same as 1/4 plus 1/3. You see? And I know that I can do this sort of thing because 12 factors into 3 times 4. And whenever someone presents you with a fraction where the denominator factors like this, you can always express it as the sum of 2 fractions where one of them is this denominator and the other is that one. So you get a common denominator, which is 12, and you get your answer. Well, we're going to do that sort of thing to this guy. But you only get to do it if the denominator factors. So here's what we're going to do. We're going to take 2 over n times n plus 1 and turn it into a sum of 2 little fractions, a over n plus b over n plus 1. Okay, so now our task is to find a and b. So let's go ahead and do it. First step is to multiply both sides by this denominator. I'm doing that to get rid of all the denominators, so I don't have denominators anymore, because denominators are offensive. So I get 2 equals. Here the n's cancel, and I'm left with a times n plus 1. Here the n plus 1's cancel, and I'm left with b times n. And then I'm going to do something that's not exactly correct, but I'm going to do it anyway and teach it to you guys anyway. I'm going to let n be 0. I'm going to argue, you know, if this is going to be true, this is going to be true for any value of n, even though obviously you're not allowed to plug 0 in for n, but I'm going to do it anyway. And so everybody in the video audience, I know I'm violating every sacred rule there is in math, but I don't care. Let n be 0. So I end up with 2 equals a. You know, 2 equals a, you know, plus b times 0. And so I'm letting n be 0, so I get 2 equals a. And that's what you're going to do. What do you suppose I'm going to let n equal now?
1?
Yeah, let's let it be -1. So I make the a go away. Thank you, Zach. -1 plus 1 plus b times -1. And so I end up with 2 equals -b, or b equals -2. So that's it. I just found how to split this fraction up. This fraction, this series, is the same as n goes from 1 to infinity of, what is my a? 2? So I've got 2 over n minus, my b is 2, so that's where the minus comes from. Minus 2, because b is minus. 2 over n plus 1. And then here comes the last step. Once I've done this, and by the way, there's a name for this process. It's called partial fraction decomposition. Partial fraction decomposition. We're actually going to see this again, and we'll be applying it to integrals. Yeah. So I want you to know there's a name for this, what we just did. We decomposed a fraction. Okay? So now I'm going to stick in my 1, n equal 1, n equal 2, n equal 3, etc. But I'm not going to combine the fractions. I'm just going to stick it in. So when I stick in 1, I get 2 minus 1. Or maybe I'll write it out so it's more clear to you. I get 2 over 1 minus 2 over 1 plus 1, which is, 2 over 2, which is 1. And then plus. Now I'm going to stick in 2. And I'm going to stick in a 2 for n, so that gets me 1, minus, and I'm going to stick in a 2 for n, so that gets me 2/3. Okay, now I'm going to stick in a 3. And please do not combine these guys. Write them out like this. I was helping a student from Mr. Morrison's class, and he was plugging in the n equals 1 and n equals 2 is n equals 3, and then he was combining them in his head as he went. And that'll defeat the whole purpose, as you're going to see shortly. So let's go ahead and plug in 3. So now I'm going to get plus 2/3 minus 2 over 4, which is 1/2. Now let's plug in 4. I'm going to plug in 4, and that gets me 1/2 minus 2/5. And I'm going to plug in 5. I get 2/5 minus 2/6, which is 1/3. 2/5 minus 1/3. Now I'm going to plug in 6. And I get 2/6 minus 2/7, which is 1/3 minus 2/7. And I can just go on and on and on. But what do you notice is happening to the terms of this series?
Cancel each other.
Yeah. Do you see they cancel each other out? I've got -1 plus 1. These guys cancel. -2/3 plus 2/3. These guys cancel. -1/2 plus 1/2. They're gone. -2/5 plus 2/5, they're gone. You see how that goes? And they're just going to cancel for the rest of infinity until finally I get to infinity and my terms are going to be 0. The infinitieth term is 0. So my answer ends up being right here. There's the answer, 2. And so that's the process. And why do you suppose they call this a telescoping series? Yes?
Because it's like when you have a telescope and then you...
Yeah, it's like a spyglass, I guess, that a pirate would use, yeah, where you go like that to look, and then when you're done, and you make it telescope down to almost nothing. And that's what happens here. All of these terms go away until you're left with the very last term, but the very last term is 0. Right? As n goes to infinity, this guy goes to 0. So you've got a term here, you got all the places that telescope in between, and then you got 0 at the end. So and you're left with that guy. Hey, you guys ready to do it on your own?
Yeah.
Yes.
So what was the purpose of the partial fraction?
To be able to do this. If I didn't do this, if I was just plugging numbers in, then the sum of 2 over n plus, n times n plus 1, okay, and n goes from 1 to infinity, I'd get 2 over, just 1 second, 2 over 2 plus 2 over, you see 2 times 3 is 6, plus 2 over, let me see, 3 times 4 is 12, plus 2 over, although I guess I could be just, well, whatever. This is 4, 6, 8, 220, 2 over 10, 30 plus. You see, so I would be adding an infinite bunch of fractions, and it wouldn't be obvious to me what the answer is. Because this isn't a geometric series, so I don't get to use my a over 1 minus r for geometric series. I'm just kind of dead in the water here. I'd have to use a calculator and see what number it gets close to. But making it a telescoping series, I get the answer immediately. Yes?
So that's what it converges to, or that's the amount?
That's the actual answer. This series equals 2. When I add an infinite number of terms, when I add this infinite number of terms, I get 2. But the only way I could have divined that would have been to do partial fraction decomposition and write out the terms and see and have a telescope on me. Then I would know, oh, it is 2. Whereas if I had just written like this, I really have no idea unless I have a computer or a calculator.
It's like direct comparison, you can't find the answer.
Right.
Well, I mean,
yeah.
without plugging in
No, you're very true. Direct comparison test and integral test, they are not providing the answer for you.
Same with
They're
nth
just,
term.
yeah, same with P-series.
And
They're just, what's that?
And term as well.
Yeah, and third, well, and third test, of course, it's diverging, so it's infinity. But all those integral test, direct comparison test, and P-series, all they're telling you is that a series converges or diverges. It's not giving you the value. Geometric series, you can get the value because you have a formula, a over 1 minus r, and now telescoping series, you get to have the value. You can not just say whether it converges or not, you can actually say what it converges to. Yes?
When you did the partial fraction decomposition, why did that n be -1?
Okay, I let it be -1 because I knew if I put a -1 in here, the a goes away. I want to choose an n such that the b goes away so I can get my value for a, and then choose an n so that the a goes away so I can get my value for b. Okay, hey, you guys ready to do it on your own?
Yeah.
Yeah.
Alrighty, here it comes. The sum is n goes from, just a second. Yeah, I can't let n be 1, so 2 to infinity. As n goes from 2 to infinity of, oh, put that at 2 on top. Because I want it to turn out all swell for you in this example first. So there it is. Good luck, guys. Do partial fraction decomposition and then write out the terms. And let's see if you can experience the telescope. Hopefully step 1 is you factored the denominator. And then you can do your partial fraction decomposition. I urge you to write out the first step. Sometimes kids want to skip that very, very first step, and then they'll end up getting A and B, and they'll put the A and the B over the wrong denominator. So it's really nice to be able to, consult with that very first step to know who do the A goes over, who does the B go over. Hopefully you got your A and your B as being 1 and -1. The positive 1 goes over the n minus 1, and the negative 1 goes over the n plus 1. And then you just plug in numbers. Alrighty. Is there any question or problem on getting A being -1 and B being 1? Or you could be the other way, depending on where you put your A and your B. I mean, you know, there's 2 ways to do it, and they're both correct. Any question or problem on this part of it? Decomposing the fraction. Okay, then you just write out the terms, and then you start to see, okay, well, who telescopes? Well, here's -1/3, and there's +1/3, right? So they're gone. And then I got -1/4 and +1/4, so they're gone. I got -1/5 and +1/5, right? And can you see, I got -1/6, I'm gonna get a +1/6, so everyone goes away. I'm left with 2 terms that didn't cancel, 1.5. So my answer ends up being 1.5. That's what that series sums up to. Yes, sir?
Does it matter which order you put 1 over n minus 1 or 1 over n plus 1?
No, that doesn't matter. And so when you have this, did you have like -1 over n plus 1 plus 1 over n minus 1? Yeah, that's fine. It'll just be the other direction, but it's okay. It's still, you're going to get all your negatives canceling with positives that are somewhere down the road. But you're going to have 2 terms that nothing canceled. Yes, Daniel?
So if n equals 2, will there always be 2 terms left over?
Not when n equals 2, but there's something else. Do you notice my factors here are separated by 1, n times n plus 1? But here my factors are separated by 2, n plus 1 times n minus 1 with a separation of 2. That's going to determine how many terms you have left over. Yeah, ordinarily I would have asked you to figure it out on your own, but yeah, that's just it. So if I were to give you like n times n minus 3, let's say, then you know you'll have 3 terms because there's 3 separate. Yes?
Why is it 1 minus, or 1 over n minus 1 instead of 2? Where it says 1.
Okay, here?
Yeah.
Because my A and my B were +1 and -1. So that's what gets to go over this. You see? I mean, the whole purpose of this is to determine what A and B are so that I can, you know, write this as an equal fraction. Yeah. I think that's it. Is there anything else I need to say? Yeah, and they don't, you know, the partial fraction decomposition can be way more complicated than this, but this is about what the AP exam requires of you. They really don't require much else, you know. So this is good enough. Well, how many people ended up getting that answer? Okay, many of you, that's good. Alrighty, well then the last thing is limit comparison test. In our remaining 5 minutes. But limit comparison test is actually pretty easy. I don't know if it's 5 minutes easy, but it's easy. limit comparison test for messy algebraic series. Okay. Oh, this might be a, okay, suppose A sub n and B sub n are greater than 0, and the limit as n approaches infinity of A sub n over B sub n equals L, where L is finite and non-zero. So L has to not be infinity, and it can't be 0 either. Okay. Then the two series, the sum of A sub n and the sum of all my B sub n terms, either both converge or both diverge. That's the point of the limit comparison test. You're going to compare two series, and if you do the ratio of their infinitieth terms, if that ratio ends up being a finite non-zero number, then they both do the same thing. Okay, here it goes. I'm going to give you one example and hope that that's good enough for you to do a few problems. Here you go, example number 1. The sum as n goes from 1 to infinity of 1 over 3n squared minus 4n plus 5. Okay? I want to know if that series converges or diverges. This is my series of interest. It's my A sub n. Now, just like with the direct comparison test, the hard part, the only hard part about this process is you've got to choose a B sub n. You've got to choose a series to compare this to where you know whether B sub n converges or diverges. So in that respect, it's just like direct comparison test. I've got to choose a B sub n, and I've got to choose a B sub n that I think is very similar to this, and I know whether B sub n converges or diverges. Okay? So you must choose the sum of B sub n. How do you make that choice? Well, I'll tell you. Number 1, you're going to choose a rational expression with only the highest order term in the numerator and the denominator with no coefficient, with 1 as a coefficient. Choose a rational expression with only highest order term for the denominator and numerator. Oh, I should write that out. Denominator and numerator. Oops. And coefficient 1. And you know what? Heck with it. I'm going to stop here. So I'm embarrassed to say your homework is just to do telescoping series. We'll do this tomorrow. It'll only take us 5 minutes, but I lost it, so that's okay. So just have this in your notes, and then we'll continue. We'll just take off where we left off. And please don't be tardy tomorrow, and I promise I won't be tardy either.
Promise?
Yes, I promise. Well, You're right, I can't really promise. Sometimes things happen.